Okay. Apparently there's a big exam tomorrow. Unit 4, Physics on the Move, January 27th, 2011. Here we go. Question 1. The area under a force-time graph represents which of these quantities? Remember, force times time, that's impulse, and impulse is equal to change of momentum. So we're definitely looking at B there. Question 2. Unit for flux linkage is which of these? So, you know, we could be looking at something related to N-phi, which is like NBA. But actually, they're just trying to tease you into looking at those units like Teslas and meter squared and stuff like that, because the unit of phi is the Weber, and it's right there. Okay, question 3. The electric field between two parallel plates is uniform. Which graph shows how the potential V varies with the distance from the positive plate? Well, parallel plates, remember, have completely uniform field. They've told us that. So remember, the electric field between parallel plates like this is uniform all the way through and is equal to V over D. So the potential at any point is going to be proportional to D, because E is a constant. So it'll be proportional to how far you are from this lower plate, your potential at some particular point. So it's going to be a linear decrease from, in this case, the example I've given is 100 volts down to 0 volts. So it's the second graph here that we're looking at. Question 4. The process by which electrons are released from a heated filament is known as one of these. Well, crucially, saying that word again, it's a heated filament. Okay? So this is what we call thermionic emission. Question 5. A particle of mass 0.020 kilograms is moving with an angular velocity of 3 pi rads per second around a circle of radius 0.5 meters. The force in newtons responsible for this motion is going to be one of these. So we remember that F is mv squared over r, but we've got an omega for this one, we've got an angular velocity, so it's also equal to mr omega squared. So 0.02 times 0.5 times 3 pi all squared. So these two, a half of 0.02 gives us 0.01. So that gives us 0.01 times 9 pi squared. So 0.09 pi squared. C. Basically because C is the one that's pointing towards the center. Away from the center is wrong. Remember, that's our definition of centripetal force. It's the force pointing towards the center of the circle. Question 6. The force on a proton at a point in an electric field is 4.8 times 10 to the minus 19 newtons. The electric field strength at that point is one of these values. So if we just remind ourselves that the electric field is the force per unit charge, so it'll be F over Q. So it's 4.8 times 10 to the minus 19 divided by the charge of an electron, only a positive version of that, which is the charge on a proton, 1.6 times 10 to the minus 19. So your 10 to the minus 19s, top and bottom, will cancel, so you've really got 4.8 over 1.6. So E is going to be 3 newtons per coulomb. And we just remember that the electric field direction is the direction of the force on positive charge. So the proton is a positive charge, so it will be in the same direction as the force. So we're talking answer D here. Okay, question 7. Which one of the following might not apply in interactions between subatomic particles? Okay, charge conservation. Well, charge is conserved in subatomic interactions. Energy conservation. Energy is conserved too. Matter conservation. That's a possible candidate. And momentum conservation. Well, momentum is always conserved in closed systems. So I think we're talking C there. And there's no reason really for the total mass of a system to remain constant, because there's energy being given to all these particles that are being fired out, and if the mass stayed the same and energy was produced, that would break some fundamental rules about conservation of mass and energy. Question 8. A pion could consist of one of these combinations. Which one? Well, crucially, we need to remember what a pion is. It's a meson. Mesons are always pairs of quarks where one quark is an antiquark. And so that rules out these baryons, these quark triplets. And the fact that one of them has to be an antiquark then rules out that one, so it could only be answer A. Question 9. Data at the back of the examination paper can be used with the formula delta E equals C squared delta M to calculate what? Okay, so the amount of energy in a proton. Well, not quite sure what they're getting at there. The mass of coal that produces 6 megajoules of energy when burnt. Well, the mass of coal relating to the chemical change there, it's not, that mass of that coal will not give you the energy it produces, because there's a mass of material left afterwards. There may be some energy conversion, but there'll be a whole load of material that we don't have masses for after you've burnt coal, so we can't necessarily get any useful information out of the mass of the coal. The energy produced when an electron and a positron annihilate. Well, that's a definite candidate for what we're looking for. The energy produced when two protons collide. Well, the masses aren't really going to be related to that, apart from the fact that the two protons have kinetic energy. So that's not really what we're looking for. And I would say that this one, I suppose the energy in the proton if you annihilate it with something, but the one that's closest to something that we're familiar with would be C. A particle X has kinetic energy E and momentum P. Another particle Y of the same mass as X has momentum 2P. The kinetic energy of Y is what? Well, if X and Y have the same mass, but Y has twice the momentum, then Y must have twice the velocity of X. And if kinetic energy is a half mv, so kinetic energy is proportional to velocity squared. Now, if Y has twice the velocity, then v squared will have gone up by a factor of 2 squared. So 2 squared is 4. So we're looking at answer D. Okay, section B then. Question 11. A particle called a B meson has been observed to decay into an antiproton plus a lambda particle. The lambda particle consisted of an up, a down, and a charm quark. The following table summarizes the charges on these quarks. Circle the correct word from the list below to describe the lambda particle. Well, firstly, we're told here that the lambda particle consists of 3 quarks, up, down, and charm. So it's a quark triplet, which means it's not a meson, it's not a lepton, it's a baryon. Baryons, remember, are quark triplets. mesons are quark doublets and leptons haven't got quarks at all. They're a separate fundamental particle. Okay, so calculate the charge on the lambda particle. So we need to look back at these charges. We're told that up, down and charmed is what it consists of. Up, you can see here, is plus 2/3, down is minus 1/3, and charm is plus 2/3. So we've got a total positive of 2/3 here, 2/3 here, is 4/3, and then we subtract 1/3. So the lambda particle will have a charge of plus 1. Okay, so you do a little calculation, adding those together, and you get plus 1. Part C, write an equation using standard particle symbols for this decay. So we need to just check what symbols we're using. We've got this B meson going to an antiproton plus a lambda particle. So we've got this B meson going to an antiproton, and the lambda we've already established is a positive thing. Now you could be fancy here, and the antiproton's negative, the lambda's plus, so you could be fancy and say that we know that that's true. Okay, question 12. The photograph shows tracks produced by charged particles in a bubble chamber. At X, an incoming charged particle interacts with the stationary proton to produce a neutral lambda particle and a neutral kaon particle. Both of these particles later decay into other particles. With reference to the photograph, describe and explain the evidence provided for this event. Okay, so the main thing here is the fact that this track just stops. Neutral particles do not cause ionization, and so they will not show a trail in the bubble chamber. Secondly, when a neutral particle decays into other particles, you will find pairs of oppositely charged particles, and that appears to be what's happening here and here. So the two particles that can't be seen are heading in these two directions and then later decay into oppositely charged, and we can see that from the curves. These things are curving in opposite directions if you look carefully at the curvature of the pairs that are produced. So the oppositely charged pairs being produced indicate that whatever made them was a neutral particle. So the vanishing of the track and the appearing of the pairs are the indication that it broke into two separate neutral particles. So you need to explain that. Question 13. Simplified diagram shows a DC electric motor. The split ring commutator consists of two copper semicircular sections attached to either end of a coil. Fixed carbon brushes rub against and make electrical connections to the split ring commutator. Explain why the coil turns and why it continues to rotate. Add to the diagram to help your explanation. Okay, so you've seen this diagram hopefully before. The coil will have current going up one direction. You can see here the current's coming in like this. That means it's heading up in this direction and down in this direction. So you have to use Fleming's left-hand rule on DC, where the current is going that way. And if you've got field going from north to south this way, you've got current going that way, you should be able to use the left-hand rule with that event to identify that this bit is pushed down. And again, using the left-hand rule on AB, and remember in AB you've got current that is coming back down here. Okay, so we put the current on in blue just to help us see what's happening. Current's coming back down on this side. And again, if you apply the Fleming's rule to that, you'll find that that particular side is being pushed up. So we get an anti-clockwise moment on this coil. And then what you have to explain in your answer is that when it reaches the vertical position, the split ring commutator swaps over which side is connected to which brush, and that reverses the current in the coil, allowing it to continue past the vertical position and make another half cycle, and then that process repeats. So you need to explain both the forces from Fleming's left-hand rule and the action of the split ring commutator allowing the current to reverse and the process to continue and repeat itself. Okay, 13b then. When the motor is first switched on, the current I is large. As the coil turns faster, the current decreases. Explain these observations. Okay, now this is linked to the coil's sort of split personality, because it thinks initially that it's part of a motor, but as it starts to rotate, it finds that it is a coil rotating in a magnetic field, and that makes it a dynamo. So as it starts to rotate, then there's a flux linkage which is being changed through it, and that produces an EMF that opposes the change causing it. So this really drags in Lenz's law. So what it starts to do then is produce an opposition to the action causing it to rotate in the first place. So this opposition is what's causing the current to be less as it rotates faster, because the opposition will increase as the coil rotates faster, because the reverse EMF caused by Lenz's law is opposing the action that's causing it. That's what Lenz's law says, and produces an EMF that opposes the change causing it. Question 14. Muons have the same charge as electrons and can be produced by particle experiments. Muons belong to a family of fundamental particles called leptons. Muons have short life decay to electrons. Exotic atoms can be produced in which muons have been substituted for electrons. For example, muonic hydrogen consists of a proton and a muon. What is meant by a fundamental particle? Okay, so remember, a fundamental particle is something that doesn't have a substructure. It cannot be made of smaller, simpler. It's fundamental. Fundamental means it's not got any kind of internal structure. That's all there is to it. It's that particle. So it cannot be split or subdivided into a simpler thing. It's as simple as it can get already. Sketch the electric field around a muon. Okay, so we have a particle, and that particle has an electric field. Now that electric field will radiate out, and what you want to do is try and draw these as evenly as you can, not having any too close, which I just did, together. And then we have to remember that this is a negative particle. And remember, the field lines point the way a positive particle would be produced. Now a positive particle will be drawn towards this, so the field lines for the muon will pull in. It's going to be true for any negative particle, because these are the directions that a positive charge would be pulled. Okay, so you want to draw those as straight as possible, as evenly spaced as possible, with the arrows pointing in. Part C. The mass of a muon is 106 MeV over c squared. Show that its mass is about 200 times that of an electron. So you want to really convert this into kilograms and then compare it with the mass of an electron from the formula sheet at the end of the exam paper. So we've got 106 mega 10 to the 6 times an electron volt in joules, which is 1.6 times 10 to the minus 19 joules, and then we need to divide by c squared. Don't forget to square it. And that gives us about 1.88 times 10 to the minus 28 kilograms. So we just put that over the mass of an electron and hope that it gives us 200. Okay, and it does, or thereabouts. Okay, 14D. Calculate the electric force between the muon and the proton in the muonic hydrogen. The distance between the muon and the proton is 2.7 times 10 to the minus 13 meters. So the force between charged particles, Coulomb's law, 1 over 4 pi epsilon naught, Q1, Q2 over R squared. So you're just filling in the numbers for that, with Q1 and Q2 being the same charge. The muon has the same charge as the proton, just the opposite sign. We're only interested in the magnitude anyway, so we don't need to worry about signs, but it's not really relevant. And epsilon naught is found in your formula sheet, and R is the value they've given here. So you're just filling that in. Okay, I'm not filling in epsilon naught because I don't have a formula sheet here, sorry. But you can fill it in from the formula sheet and check that you get the value. And the value you're looking for is like 3.2 times 10 to the minus 3 newtons. Emission line spectra in the X-ray region of the electromagnetic spectrum can be detected from the muonic hydrogen atoms. Outline the atomic processes that produce emission spectra and suggest why they are in the X-rays in this case. So you would need to talk about energy levels and excitation and return, and the idea that photons come out when that happens, and that the size of that gap is what gives that photon its energy. And so if these photons are coming out as X-rays, then these gaps must be extremely big in the muonic hydrogen. So you just need to go through that process of explaining those things. Question 15. A student sets up the circuit shown in the diagram, and you've got your sort of capacitor charging and discharging circuit here. Flick to X to charge, flick to Y to discharge. She moves the switch from X to Y. Explain what happens to the capacitor. Well, you can see that when it's at Y, the capacitor is really just connected to itself, and so any charge on it returns to a neutral state. So the plate that's positive will get electrons back from the plate that's negative through the circuit until it goes back to being neutral. So effectively the capacitor discharges through the resistor. So the resistor is going to hold that process up, and so there will be a gradual discharge of the capacitor through the resistor. On the axis below, sketch a graph to show how the current in the ammeter varies with time from the moment the switch touches Y. Indicate typical values of current and time on the axes of your graph. So we're going to have to put something on here, we're going to have to put some values. So we need to think about what happens to this circuit when you have it at X for a while and then flick it to Y. Okay, so we have got a 10 volt power supply. So if this is at X for a while, this capacitor will be at 10 volts. So when you put it into this circuit and it's discharging itself, this capacitor behaves like a 10 volt voltage source. So you can do Ohm's law here and say if you've got 10 volts acting across a 5 kilo ohm resistor, what's your initial current going to be? So you can just do I is V over R, where the capacitor pretends to be the voltage source, pretends to be a little cell, and 10 volts pushing across a 5 kilo ohm resistor. You should be able to work out that I is V over R for that. So your I naught is going to be 10 volts over 5,000, which is going to be 0.002 amps, so it's like 2 milliamps. And we can also work out the time constant while we're here with 5,000 ohms times 10 microfarads. So now we need to take those two factors down and put them on the graph. So we're starting at 2 milliamps and we are going to 0.05 there and 0.1 there. Okay, and we're going to bring that down to the 39% level. I haven't done that very well, but you want that value there to be 39%, or roughly, a third of the way up, roughly. Maybe not bring it down just so much as I have here, but that's more or less it. Obviously you put your units on. So starting at 2 milliamps and coming down about a third by the time you hit 0.05 of a second. Okay, so describe how the graph would appear when the switch is moved back to X. Well, it's still a 10 volt supply, it's still a 5 kilo ohm resistor. So the current graph, discharging and charging, always looks the same. It starts with a high value and decays away to a low value. So the graph of current here would look exactly the same whether we were at position X or position Y. It wouldn't make any difference. The current will be the same in both the charging phase and the discharging phase. Now the current will obviously flow in the opposite direction when it's discharging, so maybe that's what the second mark is for, that you have to indicate that the current flows the opposite way in the discharging phase compared to the charging phase. Maybe that's what the second mark's for. Okay, calculate the maximum energy stored in this circuit. Okay, so we know the capacitance, we know the voltage, so the easiest one to use here is half CV squared. So you've got a half times 10 microfarads times 10 volts squared. And that's going to work out a half times 10 to the minus 3 if you combine all those 10s. So it's like 5 times 10 to the minus 4. And that's in joules, obviously. Student wants to use this circuit to produce a short time delay equal to the time it takes for the potential difference across the capacitor to fall to 0.07 of its maximum value. Calculate this time delay. Okay. So we've got our discharge equation, and what we're saying here, we're being told that V is 0.07 of V naught, so we can just rearrange this slightly. So V over V naught is 0.07, and that's equal to E to the minus T over RC. Now we already found RC to be 0.05 seconds, so if we just take natural logs, then the ln of 0.07 will equal the ln of E to that, the T over RC, so the T over RC is all that's left when you take the natural log of E to something. So if we take the natural log of E to this, then we're just left with this, and we substitute what RC is equal to in that fraction. So the natural log of 0.007 is minus 2.66, and we just bring the minus 0.05 across and find the product of those two. And I'm making that 0.132 of a second. Okay, so describe the key observations of the alpha particle scattering experiment which led to Rutherford's nuclear model of the atom. Okay, so you know this. You've got your alpha particles, they come at it, most of them go straight through, tiny amount of them are deflected a little bit, and a very tiny amount of them are deflected by very large angles, and that tells us that it's a positive object in there, and the rarity of the collision that brings it through a 180-degree turnabout tells us that the object in there that can cause that is very tiny compared to the space occupied overall. So this is all fairly standard stuff. It's bookwork. You should take the time to formulate a good example answer. I'm not going to spend time doing that here. Part B then, experiments at Stanford University's Linear Accelerator. Accelerate electrons up to energies of 20 GeV. State the main features of a LINAC. Okay, so you have your drift tubes, and they get longer as you go along. And they are alternately linked to an AC supply. And you need to just explain why that is, so that, you know, this one will be positive, so this one will be positive, these two will be negative. And so that a charged particle, if we're accelerating electrons, then an electron will find itself having a forward force when it's in the right position, and that AC will reverse, so that when the electron finds itself here, this later time, the field will have reversed by then, so the electron keeps finding, for example, a positive tube in front of it, which keeps accelerating it forward. Part 2, calculate the de Broglie wavelength of 20 giga-electron-volt electrons. At these energies, the following relativistic equation implies that E equals PC. So de Broglie told us that the lambda was H over P. We also have the idea here that P is going to be E over C, and so we need to substitute that in, and we divide H by P. We're going to get HC over E, just subbing that in. So we've got 6.6 times 10 to the minus 34 times the speed of light divided by 20 giga. Okay, and that's not HE, that's not an SI unit, so we need to convert that by putting an electron volt in joules. So that should be giving us the lambda we're looking for now. Okay, so that should come out to be 6.2 times 10 to the minus 17 meters. Please take the time to check that. I'm not even using a calculator here. Suggest why these electrons would be particularly useful for investigating nuclear structure. Well, you know, this diffraction question, these things have a tiny wavelength, and so they would be useful for probing the nature of what's going on inside a nucleus, because these are the kind of distances that we might come across. It's certainly smaller than the nucleus. Nucleus, remember, is around about 10 to the minus 14, so this is quite a bit smaller than that, and so that's why they would be useful. Okay, these electrons are aimed at a hydrogen target. Some of these electrons are scattered at large angles by the protons, whilst others pass straight through. This is just a microscopic version of Rutherford's experiment. Okay, this is telling us that there are centers of collision inside the proton, that it has some structure underneath the outer appearance of a single particle. So this is a version of Rutherford's experiment at a smaller scale. So there are scattering centers within the proton. We know that those are quarks, but this evidence is telling us that there are objects in there, and that's what the discovery of the quarks was about. Okay, the scattering process is inelastic. What is meant by an inelastic collision? Remember, an inelastic collision is one where kinetic energy is not conserved. That's just straight bookwork. Question 17. A cyclotron can be used to accelerate charged particles. You can see here we have the Ds with an alternating potential difference between them, and we have a vertical magnetic field. Explain the purpose of the magnetic field in a cyclotron. You may add to the diagram if you wish. Okay, so the magnetic field there to produce a centripetal force on any charged particles and cause them to go round in a circle as we accelerate them. Okay, so it's helping to provide the centripetal force to allow us to move them in a circle. A beam of low-speed protons are introduced into the cyclotron. Show that the number of revolutions per second f completed by the protons is given by f equals EB over 2 pi m. Okay, this is the standard sort of derivation of the cyclotron frequency. Okay, so the Q here is the electron charge. So instead of BQV, we can say that BEV is equal to the centripetal force value of mv squared over r. So dividing through by v gives us that BE will equal mv over r. And we just remind ourselves that v is equal to r omega, and that omega is 2 pi f. So BE will equal m, and instead of v now we have 2 pi fr over r, and those r's cancel. So f is going to equal BE, or EB as they have put it, over 2 pi m. And that's what they asked us to do. Okay, part 2. An alternating potential difference is placed across the two Ds to increase the energy of the protons. Explain why the potential difference that is used is alternating. Okay, because the protons, every time they cross the Ds, they're crossing the Ds in the opposite direction, because the Ds are sitting like this, and the protons are making their way in a spiral around this. So every time they cross it, compared to the last time, they're crossing it in the opposite direction, so they will need a reversed voltage to make them accelerate as they cross that gap each time, and that's what you need to be explaining. Initially, whilst proton speeds are low, the frequency at which the potential difference has to alternate is constant. Explain how the frequency must change as the protons gain more and more and more energy. Okay, so the frequency that we had previously had m in it, and as these protons go faster and faster and they approach relativistic speeds, m is not a constant, and therefore f is not a constant. And so that's what you need to explain. As the protons go faster, m will start to change because of relativistic effects, and that means that f will no longer be a constant. Okay. In the Large Hadron Collider at CERN, protons follow a circular path with speeds close to the speed of light. X-rays can be produced by free protons which are accelerating. Explain why this provides a source of X-rays even though the speeds of the protons are constant. Okay, so this is the fact that they're moving in a circle. This is taking us back to the circular motion and the fact that an object moving in a circle does not have a constant velocity, even though it has a constant speed. Because its direction is changing, its velocity is changing, and therefore that particle is accelerating. So protons moving in a circle are accelerating, and therefore they will produce these rays. 18. A student is using a Newton's cradle. This consists of a set of identical solid metal balls hanging by threads from a frame so that they are in contact with each other. She initially pulls one of the balls to the side as shown. She releases the ball, it collides with the nearest stationary ball and stops. The ball furthest to the right immediately moves away. So hopefully you've seen a Newton's cradle before. And they go click, 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 back and forward. Explain what measurements the student would take and describe how she would use them to investigate whether momentum had been conserved in this event. Okay, so you're going to want to know if this one comes down and this one goes up, does this one have the same momentum as that one? So you would need to know the mass of this and the velocity it hits here with, and the mass of this one and the velocity it leaves with. So I suppose the potential energy, the height drop of this one, would allow us to work out its velocity using conservation of energy between the potential here and the kinetic here. And then you could do that in reverse. The kinetic here would allow us to give us an estimate of the potential, because the potential made here is telling us the kinetic it had here. So you would have to make some measurements of the masses of the balls and their used conservation of energy to work out their velocities here and here, and that would allow you to then do a calculation to see if momentum was being conserved. Okay. Part B, the student makes the following observations. The ball on the right returns and collides with a similar result. This repeats itself a number of times. After a while, the middle balls are also moving, and shortly afterwards the balls all come to rest. Discuss these observations in terms of energy. Okay, so these are inelastic collisions, which means kinetic energy is being lost and converted to other forms. You will hear them clicking, and there's probably heat being produced in the collisions as well. So there's energy being lost from the system, so that explains why after a while it does come to rest. It's not a perfect system. You can hear it, it's losing energy. So, that's the most obvious thing that's happening there. Okay, and that's us done. But I'm really sorry, this has been done in a massive hurry because I want to upload it where there's still a reasonable amount of the evening left. It's 20 to 10, so I want to get it up there so that anyone who's subscribed can get to see it before their exam tomorrow. So good luck everybody, all the best for tomorrow.